This is Resonance and Formal Charge 2.6. Our outcome is I can represent a molecule with a Lewis diagram that accounts for resonance structures or that uses formal charge to select the most likely structure. So first thing that we have is a data table, which is giving several molecules. I've got ethane, ethene, and ethine, so a single carbon-to-carbon bond, a double carbon bond, and a triple carbon bond. And then I have benzene. So we're looking at the bond order that's predicted from the Lewis structure and looking at the bond order that's been calculated, as well as the calculated bond length. So what is the bond order for ethene? Why is it 2? Because it has a double bond. So looking at ethane, ethene, and ethine, what is the relationship between bond order and bond length? So we see that as the bond order is increasing, that the bond length is decreasing. So C is asking us to predict what the bond length would be for a molecule if it had a bond order of 1.5, a carbon-to-carbon bond with an order of 1.5. So ethane is bond order 1 and ethene is bond order 2. So bond order 1.5 is going to be somewhere in the middle of those two bond lengths. So I guessed around 141. So experimentally, we find that all 6 carbon-to-carbon bonds in benzene have the same bond strength and the same bond length. So is this more consistent with the bond orders that are predicted by the Lewis structure versus the calculated bond orders? So in the Lewis structure, we would expect to measure 2 different bond energies. One would be for the double bond and one would be for the single bond. But instead, we see that all of those bonds have the same energy, meaning that they must all have the same bond order. So that's more in line with the calculated bond orders. So which feature of the Lewis structure of benzene is inconsistent with those calculated bond orders? The Lewis structure shows 2 different types of bonds, 2 different bond orders, but experimentally we see that there's only one bond order and all of the bonds are the same. So how could that be? This comes from resonance structures. So the structures that I'm showing here are resonance structures indicated by that double arrow. The best description for the structure of a molecule is the average of the resonance structures. So for resonance structures of benzene, the carbon-to-carbon bond order is 1.5, and the properties of that bond are somewhere in between a carbon-to-carbon single bond and a carbon-to-carbon double bond. So based on that resonance hybrid model, why is that carbon-to-carbon bond order 1.5? So the resonance hybrid model shows multiple structures that can be averaged together. So since the single and double bonds switch location, the average is 3 divided by 2, which is 1.5. This is supported by the experimental evidence that all bond energies are the same. So we have to remember that the electrons that are shared in bonds are not static. They can move, and their movements impact electron density across the entire molecule due to electron repulsions. So that means that the movements of those electrons impact the properties of the bonds. So it's not just that I took structure A and rotated it slightly and called that structure B, it's that the actual bond is changing between a single and a double bond. So based on the calculated bond order and bond lengths of benzene, which representation is better, the single Lewis structure or the resonance hybrid model? So using that resonance hybrid, that average model, our model better matches experimental results. So keep in mind what makes something a better Lewis structure is how well does it predict and match what we would see experimentally for those bond orders and bond strengths. So we could further test and improve this model by seeing if we can predict bond energies for other molecules with resonance structures. So in question 5, it asks for us to give the other resonance structure for cyclobutadiene. And based on the structures, the bond order that we predict is going to be about 1.5. And that's because that bond is switching between single and double bond. So if I wanted to predict that bond order, again, I'm looking for something that's going to be in between a first order carbon-to-carbon bond versus a second order carbon-to-carbon bond. So sometimes we're able to draw more than one possible Lewis structure that follows all of our rules. So how can we predict which one is better? So the purpose of a Lewis structure is to give us a simple model from which we can make predictions about molecular structure and properties. So sometimes there is more than one possible Lewis structure for a molecule. So looking at structure A and structure B, both of these have everybody's octet satisfied. They follow all of our rules. Both of these structures could be correct. But we can use formal charge to determine which one is the most useful. And again, that means the one that best predicts our experimental results. So the best Lewis structure, or Lewis structures, if there's a resonance hybrid, is the one with the lowest formal charges that also obeys the octet rule. Generally, we don't see formal charges greater than plus or minus 1 on good Lewis structures. So to find the formal charge of an atom in a molecule, so we need to assign electrons to each atom. So non-bonding electrons are assigned to the attached atom, and shared electrons are divided evenly between the bonded atoms. Then, to find the formal charge, it's just going to be the core charge minus the number of assigned electrons. And we should note that the sum of the formal charges will always equal the total charge on the molecule or ion. So here I'm going to calculate the formal charge for water. So this is the best Lewis structure for water, but we're going to go ahead and calculate formal charge. So for the hydrogens, the core charge is plus 1, and each hydrogen here just has this single bond. So that means that we're going to divide those two electrons. One of them will go to the oxygen and one of them will go to the hydrogen. So that means that I have one assigned electron for each hydrogen coming from that single bond. In the case of oxygen, I've got 1, 2, 3, 4 lone electrons plus 2 from these single bonds. So that'll give me a total of 6. So whenever I solve this, I end up with formal charges of 0, and everybody follows the octet rule. So I know this is a good structure for water. So looking at those two possible Lewis structures for carbon dioxide. So in structure A and B, I went ahead and just labeled this as oxygen 1 and oxygen 2 so we can keep track. But when we calculate the formal charge on both of these molecules here, we see that in structure A, all of our formal charges are equal to 0. So the oxygen has a core charge of plus 6. It's got these 4 lone electrons, and then the 4 electrons in the double bond, I'm going to assign half of those to oxygen and half of those to carbon. So I end up with 4 on the carbon, 6 on each oxygen. We get formal charges of 0. In structure B, I've got 6 lone pair electrons on this oxygen plus the 1 that I'm going to get from this bond. So I end up with -1 and +1. So structure B is not as good of a structure as structure A. It does not match our observations as well. So in fact, we see that whenever we measure those bond energies, we find that they both have the same bond energy. So that matches structure A better because both of those bonds are equivalent in structure A. So this again supports that structure A is more useful because it better matches our experimental observations. Here are two Lewis structures for formic acid. So once again, I numbered the hydrogens and oxygens so it's clear which one we're talking about. But in structure A, you end up with 0 formal charges, and in structure B, we get a +1 and a -1. So that means that structure A is the better structure here. So the carbon to oxygen bond length with no hydrogen attached, so that's this guy right here, is 124 picometers, and the carbon to oxygen bond with hydrogen attached, so that's this one over here, is 131. Does this agree with your answer? So the longer carbon to oxygen bond should be the single bond. This agrees with structure A, where the carbon to oxygen bond with the attached hydrogen is the single/longer carbon to oxygen bond. So here is the Lewis structure for ozone, and it actually is best described by a resonance structure. So based on the resonance structures, the bond order we predict would be about 1.5. So what we see here is that the oxygen to oxygen bond length in ozone is right in between the bond length values for an oxygen to oxygen single bond or a oxygen to oxygen double bond. So this bond length value is in between that of a single and double bond, which again matches our resonance hybrid model. We can also now look at drawing Lewis structures for polyatomic ions. So remember that a polyatomic ion is really just a covalent molecule that behaves like an ion, meaning it's got a charge overall. So nitrogen has 5 valence electrons. Oxygen has 6 valence electrons, and there's 3 of them, which means 18. So far I have 23 valence electrons. But if we make this the nitrate anion with a -1 charge, we add another electron, and that gives us 24 valence electrons. So in order to calculate the total number of electrons on a molecule, it's going to be the valence electrons minus the charge. And if you have a negative charge, like we do in this case, you end up with a -1, which of course becomes positive. So why is a resonance structure better than just a single structure? So our experimental results show that all 3 of those nitrogen to oxygen bonds have the same bond energy. So the bond order for nitrate is 4/3. So this is calculated by taking the total number of bonds and dividing it by the bonding atoms. So in my ozone molecule, in my nitrate molecule, I've got a double bond and 2 single bonds. So that's 4 bonds total, and then I've got 3 bonding atoms, these 3 oxygens. So I predict that the bond order should be about 1.3 for nitrate. So this is the nitrite ion that we're looking at next. The best Lewis structure is going to include 2 resonance structures. Draw them and label them with formal charges. So I first calculated my total number of electrons here. I end up with 18 electrons total. So my Lewis structures that I've drawn are going to be a resonance structure, and that double bond location is going to switch. So we get a bond order of about 1.5. Now if I look at the formal charges for both of these Lewis structures, they should add up to -1 because that's the charge on the ion. So what has a shorter end to O bond length? Nitrite or nitrate. So the bond length in nitrate is a little bit shorter. It's about 1.3, whereas in nitrite, it's about 1.5. So atoms that are in the 3rd, 4th, and 5th periods can have extended octets of more than 8 electrons. So looking at these 2 Lewis structures, we want to confirm that the formal charges are 0. So I did it for xenon and oxygen, phosphorus and chlorine. All of the oxygens and the chlorines are the same here, so I just did one calculation, but we can see that both of them end up with formal charges of 0. So what is the sum of the bonding and non-bonding electrons for each of those central atoms? So for xenon, it's 16, and for phosphorus, it's 10. So we're breaking this octet rule, and we're able to have more electrons, but still have good Lewis structures with formal charges of 0. So why can carbon, nitrogen, oxygen, fluorine only accommodate 8 electrons? So when you write out the electron configuration for these elements, only the s and p orbitals are available for bonding in the second energy level. So the s orbital can hold 2 and the p orbital can hold 6 for a total of 8, a full octet. But atoms that are in the third or greater period can accommodate more than 8 valence electrons, and that's because they have the s, p, and d orbitals available for bonding in the third energy level. So I've got 2 from S, 6 from P, and 10 from D, which gives us a total of 18 electrons. So we can actually have Lewis structures that break the octet rule for atoms that are in the third or greater period. So the SO3 molecule is going to have 24 electrons, and we have to keep in mind here that the sulfur can break the octet rule. It can have more than 8 electrons. So here's my Lewis structure where I've moved several of the lone pairs on oxygen into double bonds, and my formal charge here all works out to 0. And based on the bonds for S to O, it's going to be bond order 2. So your reflection questions, revise and finalize your checklist that you made for Lewis structures from topic 2.5. Add information about resonance and formal charge. How does this concept of resonance structures improve the Lewis structure to better match experimental data? So this matches what we see experimentally for bond length and bond order. Instead of it being 2 separate bond lengths and bond orders, we see that in things like benzene, that they all have equivalent bond order and bond strength. So what criteria should you use to best determine which Lewis structure is the most useful? So remember, we've got to check for those octets. We also have to check for formal charge. We have to check for resonance structures. And we also have to be aware that we could have extended octets beyond our typical 8 electrons.